Welcome everyone to the 2024 Vision Spectra Conference. Thank you all so much for joining us, and in this session you will hear from Martin Ettenberg, the CEO and founder of Princeton Infrared Technologies, which is dedicated to developing NIR and SWIR detection technologies. Martin graduated from the University of Virginia Department of Materials Science and Engineering with a doctorate degree and has over 25 years of experience developing in-gas detectors. Today he's helping viewers understand the importance of signal-to-noise in SWIR Hyperspectral Imaging. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me, Martin. We appreciate you taking the time to present at the 2024 Vision Spectra Conference.
Thank you very much. Thank you for the introduction. Let me get everything rolling. All right. Today I'm going to talk about the importance of signal and noise in SWIR imaging, and my little subtitle, why is my SWIR image black, which is always the question that people usually ask me on these things. So today I'm going to give you a little talk on this, and we go from here. So a little agenda on today's talk. First, I'll give an introduction to what shortwave infrared is, or SWIR as we call it. Then I'll talk about why we care about the shortwave infrared region. I'll give you some definitions so we can define things and explain things. I'll explain a little bit about current camera technology and camera terminology. Then I'll go into a signal and noise discussion, and then I'll conclude my talk. So let's talk about SWIR technology in general. So SWIR stands for the shortwave infrared. It's defined from about 1,000 nanometers to 2,600 nanometers. At 2,600 nanometers, that's traditionally where glass cuts off. There's also a water absorption line out there, so it's hard to image on Earth beyond 2,600 nanometers. There's also the near infrared range, so our eyes work from 400 in the blue and violet to 750 nanometers in the red. Anything beyond that, they actually consider from 750 to 1,000 nanometers the near infrared, which is basically covered by silicon. For years, lattice match InGaAs was and still is the preferred material for detecting in the shortwave infrared, and this is done on indium phosphide substrates. The advantage of this material is it can see from 400 nanometers in the visible all the way to 1,700 nanometers, covering a bunch of the shortwave infrared. To go up beyond that, there's some lattice mismatch InGaAs, which is used, which is high dark current, or typically mercury cadmium telluride or indium antimonide are used. The problem with those detectors is they're very expensive and they require significant cooling, which makes them even more expensive and heavy and powerful. In the last couple of years, we've seen a new array of materials called these colloidal quantum dots, or CQDs. They're a low-cost alternative to indium gallium arsenide detecting in the shortwave infrared. They do have the advantage of being very low cost, also can be made on very small pitch. The downside is they have very poor sensitivity and higher noise. So they're not nearly as sensitive, but there are lower costs. So depending on your application, a CQD may be advantageous for you to use in imaging shortwave infrared. Just to explain to you, shortwave infrared is different, and we see from this example where shortwave infrared is beyond the visible region, which we see. And it's different than the infrared what people typically think of, which is like body heat, which can be seen in the midwave infrared, which is 3 to 5 microns, or long wave infrared, which is 8 to 12, which are generally done with microbolometers or very cooled mercury cadmium telluride. Just to give you more of an example, looking at reflected versus emitted light, the midwave and long wave infrared is almost entirely done with emitted light. So the object is hot or relatively hot, and it emits light, and that light is detected by these midwave and long wave infrared detectors. Visible and shortwave infrared mostly use reflected light. Granted, there is emitted light too, a light bulb or the sun. Those are sources of emission. They're hot enough to actually be emitting light in the visible spectrum or in the shortwave infrared spectrum. And then in the shortwave infrared and visible, we see that light reflect off objects and then we image with it. And so in this case, the person here, we're seeing the reflection of light and the person's hair is dark. In the shortwave infrared, you can actually see their hair is light, and that's because the reflective properties in shortwave infrared is different from the reflective properties of visible. And this is one of the reasons why shortwave infrared is used, is you can actually differentiate objects sometimes very easily because the reflective properties are different. Now, shortwave infrared can also see emitted light, of course, at a much lower temperature than what you could see in visible. Obviously, something has to be very hot, like red hot, for you to see it in visible, but it has to be a lot less hot for you to see it in shortwave infrared. And then obviously even less hot because you can see body heat in midwave and longwave infrared. And in this case, you can see the person's emitting and their hair is darker in this case because it's not emitting as much. It's because it's colder, so it's darker. So you can see there's different reflection and emission properties as you move across the infrared band, and these allow you to differentiate different materials. So how do we do this detection? So we do what's called with a focal plane array, and what a focal plane array is, it's very similar to our silicon CMOS cameras that we carry in our pocket in our cell phones. So these silicon CMOS cameras are built with silicon, obviously, but they have a detector pixel in a detector in each pixel, and that allows us to convert the photons that come into an electrical signal, and then it's converted and amplified in the silicon CMOS circuit. A readout integrated circuit that we use is basically the same thing as the silicon CMOS cameras, but instead of having a detector pixel there, we remove the detector. We put more circuitry in there, and we actually put a landing pad to make an electrical connection, and we electrically connect it to our detector material, which is shown here. In this case, we're using InGas as the detector material, and this sits on top, and it's connected at each pixel with small little indium bumps or other metal as a connection. And so then each pixel is physically connected to the detector. And so you ought to think about these readout circuits very similar to how you think of a silicon CMOS, except instead we put this detector material on top, which allows us to detect different wavelengths of light. And you can see here, this is one of ours. The gold part is the actual InGas detector, and then the silicon CMOS sits underneath it. It's a little bit bigger and allows us to wire bond out for all the electrical connections. So why do we use this SWIR? Well, it's phenomenology that we can see in the shortwave infrared that we can't see in the visible. So in this case, we have 4 liquids here, all look clear. They look all the same to our eyes, but TCE is very different from water as acetone. And originally I had my engineer set up this picture, and it was supposed to go from lightest to darkest, and I was upset when he took the picture because the isopropanol I assumed he put in the wrong spot. And I was yelling at him that he mixed it up, and he swore he didn't. And we looked at it and it wasn't. But we found out actually that he used isopropanol, not a fresh isopropanol from the bottle, but something that's been sitting on the bench for over a month. And it ends up that isopropanol was absorbing water from the air. And we're actually detecting water in the isopropanol alcohol. Water is darker at 1400 nanometers in the shortwave infrared because it's very absorbing at 1400 nanometers. So the water you can see is dark. But in this case, the isopropanol wasn't supposed to be that dark, but because there's water in it, we're actually picking up the detection. So instead of fixing the picture, I liked it so much at this point because now I have a story, and that's why I use it in this case. So you can actually tell the difference of the water absorption, and that's one of the big reasons shortwave infrared is used, is because we can detect water very easily because of its absorption properties. But there's other things you can do sorting and spectroscopy, and by looking at reflectivity at various, or absorption at various wavelengths, we can look at peaks and valleys. In this case, these are various salts. And by looking at different wavelengths of light and looking for peaks and valleys at these different wavelengths versus others, we can actually do spectroscopy and actually differentiate material A from material B. Even though they may look the same to our eyes, we can actually use these wavelength differences to actually sort materials. And that's what shortwave infrared is used for in many applications. So in this case, this is coffee beans versus contaminants, right? So all these coffee beans are brown. The contaminants are, wood, rocks, all these things are also brown. It makes it very difficult for a visible camera to tell the difference. But in the shortwave infrared, the coffee beans are quite bright at 1400 nanometers, and the wood and the rocks are dark. And so we're able to actually sort the difference between the coffee beans and the woods and rocks. And this is just a simple sorting application that's done. As I said, we can also see thermal emissions. And the nice thing about shortwave infrared is we can actually see thermal emissions through glass. That's something that a long wave and mid-wave camera can't, because as I said earlier, glass only works to about 2600 nanometers. After that, it's no longer transmissive. And so in thermal cameras like mid-wave and long wave, you're actually only seeing the temperature of the outside of the glass. But in shortwave infrared, we can actually see through glass the thermal emission. So in this case, this hot liquid, we could see through the glass. This is a black body source at 100 degrees C, and we see right through the glass. While the thermal camera can't see through the glass, it only picks up the temperature of the glass. In this case, we also have a soldering iron. We can see the soldering irons on in the shortwave infrared because it's emitting light. With this long wave infrared camera, you actually see more of the temperature differences, so you can actually see the temperature all the way up to the handle because it's having thermal emission there. But we're not looking. In this case, it's using a germanium lens. So another advantage of shortwave infrared when it's used. So let's talk about how we talk about these cameras. So one of the biggest things we talk about in these detector systems and these cameras is quantum efficiency. So what is quantum efficiency? Quantum efficiency is a description of how many photons we actually turn into electron hole pairs, or actual signal that can be measured by our detector. So when we say a material has 80% quantum efficiency, what we're saying is if 10 photons come in, 8 of them are converted into electron hole pairs, which we could then measure as signal. So a higher quantum efficiency allows you to convert more of your light into real signal. So InGaAs has very high quantum efficiency in shortwave infrared. As you can see here, it's above 80%. And it rolls off once you get into the visible spectrum, but it's still very high. You know, you're talking about 60–70% across most of the range. InGaAs, mercury cadmium telluride, all in the SWIR band have very high quantum efficiency. Even germanium, which is used in some detectors today, also has relatively high QE. Not as good as InGaAs, but good. These CQDs, which I talked about earlier, I'm showing the quantum efficiency here, is significantly lower. And so, granted, we're talking about a low-cost device. They are improving and they're making many strides in quantum efficiency, but the commercial cameras out there are generally in this low quantum efficiency area. And so, you know, water absorption somewhere around 1350, 1400, you're only talking about 77 or 8% quantum efficiency versus 80%. So you're talking about a factor of 10 in signal gain at that point. So if you have 10 photons coming in, you know, only 0.7 of them are turning into signal. So it's a loss of signal. So if you have a low signal flux, a CQD is not a good material to use because you're throwing away a lot of that signal. The other important thing to talk about in these cameras is what we call full well. So a full well is basically, you ought to think of it as a bucket. So each pixel in the camera has basically a bucket or storage of charge. And we define this in terms of either electrons or volts, depending on the camera specifications. But basically, we're talking about how big this bucket is and how much charge we can store. And then we have an A to D on the camera that actually divides this bucket into pieces. And that's what the A to D does. It actually divides it up and tells you how full it is in digital counts. The key is you don't want to saturate your bucket. So if you saturate the detector, then you don't know how much signal is truly coming in, because if you hit saturation and one more photon comes in, you don't know whether only one more photon has come in, or 1,000 or 10,000 or 100,000 have come in, because you've already saturated the detector. It just shows saturation. So, but it doesn't indicate how much more beyond saturation you are. So you always want to keep the amount of signal you have, total signal you have, under saturation. You can go near it. Generally, we like to say at 95% of saturation at most, because once we start getting near the top end percent, usually there's some non-linearities. But once you hit saturation, information is then lost at that point. So you never want to oversaturate your detector. Now, the other control we have is what's called integration time and frame rate. We ought to think about it. Integration time is the amount of time that your imager is actually capturing information. I'm dating myself because I'm a little older. I don't know how old the audience is here, but back in the old days, we used to have film cameras. And what happens is you press the button on the shutter, and the shutter would actually physically open for an amount of time and then close. And the amount of time it was open was the amount you exposed your film. And the longer it opened, the more you expose your film. Same thing with these electronic detectors, except we're just using electronic shutters now. We're actually throw a switch in each one of these pixels, and now we're actually collecting signal during that integration time. Now, the integration time could be as long as you want, but it has to fit inside the frame time. You can't have an integration time longer than your frame time. So it's got to be slightly shorter than your frame time. And then between each frame in these imagers, you have what's called dead time, which is when we do some reset and moving around a charge. And so there's usually this dead time between frames, which can be very, very small, but there's something between them, right? So your integration time, though, can be much shorter than your frame time. That's allowed. But then you have what's called dead time when you're not integrating. So something could be happening in your scene, but the camera won't be seeing it. Longer integration time allows more signal to be captured. The downside with long integration times is you start to have what's called blur, because if you have something moving in the scene, it could, if you're integrating for a longer time, it could actually move from pixel to pixel, and that will actually cause a blur in your image. So there's these trade-offs. Longer integration time gives you more signal, but it also can create more blur, especially in a machine vision kind of application. So as we said, signal's important. The goal is to convert as many photons coming in into signal. And this is important because you may have filters in front, you may be doing polarization, you have your lenses. There are a lot of things that are actually removing signal from the system. So you want to capture as much of that signal as possible. Now, larger pixels allow for greater capture of photons. Longer integration time also allows greater collection of photons. The downside is larger pixels lead to larger arrays, which means bigger objects. Also, it's a more expensive detector when you have a larger pixel pitch. So if you have these larger pixels, in this case, you're paying for more InGaAs, it's a more expensive detector. Longer integration times allows you to capture more signal, but at the same time, it leads to slower frame rates. So you can't capture as many frames of data. And also, if an object's moving in the scene, you could have more motion blur. So there's these various trades you have to make with longer integration time. As I said, pixel size is important. Larger pixels capture more information. So if you have a 12 micron pixel, you get 144 micron square of area you can collect signal from, versus a 5 micron pixel, which only has 25 micron square of area. That's 5 times more signal you're capturing in each pixel. The other advantage of large pixels typically is you can fit more circuitry in each pixel. So generally, that's not always true, you could have a better amplification system, which leads to lower read noise, which I'll get to in a moment. So noise. So in these imagers, we basically talk about 2 major noise sources. There's read noise and then shot noise, So read noise is the noise that's generated every time the signal's read out. So every time you have a frame of imagery, no matter what the integration time is, you have this fixed amount of read noise, and it's based on the camera or the imager itself, usually depending on your capacitor size or the amplification circuitry. It's a fixed number, and it's there every time you read out. On the other side, you have shot noise. Now, shot noise is noise that's generated from signal. Now, it could be good signal that's coming into your camera, and also I'll talk about in a moment dark signal, which is signal that's produced by the detector even in the dark. Any type of signal that comes in, dark or urea signal, actually produces shot noise, and it's the square root of the signal. So the more signal you have, the more shot noise you're going to have. And this is important because integration time, as I said earlier, produces more signal, but it also produces a chance for more noise. So integration time directly affects shot noise. It does not affect read noise. So as I said, the read noise is dependent on your amplification circuit. It's the noise that comes out every time you read. And I have some examples here. So like if you have a readout circuit with a high gain mode, let's say it has a full well of 22,000 electrons. But in this high gain mode, it's got a read noise of only 25 electrons. You go, oh, that's pretty good. Versus your low gain mode, which only has 470 electrons of noise. And you're like, wow, that's a lot more noise. But The full well is much bigger, 1.1 million electrons. The ultimate signal noise you can achieve is the ratio between that full well and that read noise. That's the best signal noise ratio you can achieve. Now, in this case, the high gain mode only gives you a signal noise ratio at best of 880 to 1, while the low gain mode can give you 2,340 to 1. Now, you can get a better signal and noise ratio on the low gain mode, but you have to have enough signal to actually achieve it, because you're going to have to overcome that larger read noise of 470 electrons. Now, as I said, the other thing is dark current, which is very important. So photodiodes, all of them in the world, all produce dark current. Now, and that's because every photodiode that sits above absolute zero, and since we can't get to absolute zero, then we're going to always have dark current. Now, it could be very, very small at low temperatures, but you're still going to have it. And this is a signal that's produced from defects in the diode, and it's a noise source. So we try to minimize this dark current as much as possible, this dark signal. And the longer integration time you have, the more of this dark signal you collect. Now, the noise from the dark signal is always the square root of signal. So the more dark signal you create, remember, is not great, but the noise is the square root of it. So longer integration times, as long as you have enough signal coming in, is beneficial. But it also is filling your full well. So in this case, you're seeing the red is dark signal. As you go to longer integration times, you will fill more of the full well with more dark signal. But also, it allows you to collect more photon signal. So this dark current is unwanted signal. It's there, you have to deal with it, and it contributes to your noise source. It's important to keep track of. So we look at these systems as through what we call a photon transfer curve, and this allows us to look at and analyze these systems. And so the total noise of a system is you add all the noise in what's called quadrature. So the square of the read noise plus the square of the dark noise plus the square of your signal noise plus the square of any other noise sources you may have are all added together, and then you take the square root of that, and that's your total noise. So when you're at very low signal levels in an imaging detector, you're dominated by the read noise. That's the main noise source. And so you get this flat line of noise versus the noise squared versus signal. As you increase your signal level, whether it's dark signal or dark noise, or whether it's from your signal noise, whether it's dark current or signal current that's coming in, you start to produce more noise from that signal. And eventually that noise begins to dominate over the read noise, and you start to see noise that pops above it. And that creates this part of the curve, which is the shot noise due to signal. And so we produce these curves to actually measure the read noise and then the shot noise of the system. So let's look at some examples. So we have two cameras, one that's cooled and one that's uncooled. So an uncooled camera, 20 degrees C, let's say, produces 50 kiloelectrons per second of dark signal. But when you cool the camera, you reduce significantly the amount of dark signal that's created down to 500 electrons per second. And let's put a fixed read noise on this camera, because it doesn't matter. Read noise doesn't really change very much versus temperature. And as I said earlier, it doesn't change versus integration time, right? So if you have this dark signal at 20 degrees C and you have a short integration time, you don't capture a lot of this dark signal. So if you're doing fast frame rate, with let's say 200 frames per second, only 5 millisecond integration time, you don't capture a lot of dark signal, and so your total noise isn't that high. It's mostly dominated by this read noise. But on the other hand, if you go at a slow frame rate, like if you have it on a microscope, you're going 10 frames per second, and you go to a long integration time, you capture a lot of dark signal at room temperature. And the dark noise then begins to dominate, and now you're dominated by your noise from your integration time. Now, if you have a cooled camera, the short integration time doesn't affect you at all, because your dark signal is already very low. So short integration time, you're collecting infinitesimal amount of signal. But you can do very, very long integration times with a cooled camera because now you're not collecting very much dark signal and you're still mostly dominated by this read noise. And so depending on your application, you may not need a cooled camera or you may not need a low dark current camera, depending on whether you're doing very fast integration times or whether, but if you're doing very long integration times, you want to knock down that dark signal as much as possible so you can reduce your noise as much as possible. So now we get into the signal to noise ratio, and that literally talks about how good an image you have. So we look at the signal, the amount of signal you come in versus this noise. So it's total signal versus total noise, and you'll see now, I'll show you the actual effect of the signal to noise ratio. And the best way to look at it is with pictures. So in this case, on the top row, you're seeing signal to noise ratios of less than 1. And basically, you have a black image. Your noise is dominating. You can't see anything. It's just snow and nothing. And even when you get to a signal noise ratio of 1, it is very hard to actually differentiate and see things in the image. What you really want to have is signal noise ratios of much higher than 1, somewhere in at least the 10s, most likely the 100s, and you'd really love to get into the 1000s because you're actually able to differentiate various parts of the scene much, much better, especially if you're using computer algorithms, which the human eye is doing some image processing to be able to see in the scene, but a computer, you're using a lot more image processing if you have to deal with a low signal noise ratio. It's harder to differentiate that there are rocks here and the waves and the clouds versus when you go to 1,000 times where you actually really could start differentiating parts on the rock and so forth. And so signal to noise ratio really affects you in this case. So now I did a comparison of 3 cameras. So camera A is a small 5 micron pitch camera with in-gas with a higher read noise. It's a low cost camera because of the small pixel pitch and the higher read noise, but it's still in-gas, which has very high quantum efficiency. Camera B in the shortwave infrared, which coincidentally is the camera we sell at Princeton Infrared Technologies, is a 12 micron pitch camera, larger pitch, higher quantum efficiency because it's in-gas, but it has a much lower read noise than camera A. Camera C is these low-cost CQD cameras, which has even bigger pitch for more capture of light, but has a very low QE, has higher dark current, but it does have a lower read noise because of the large pixel pitch. You're able to fit more electronics in there. So if you look at a low signal flux, like in this case, 0.8 milliwatts per meter squared, and you're looking at 1400 nanometer light, and we plot signal to noise ratio versus integration time, and these integration times lead to different frame rates, we're able to see it's a very big difference between the signal noise ratio of, let's say, a 12 micron pitch in-gas camera versus a 5 micron pitch in-gas camera. The 5 micron pitch in-gas camera, even at 30 hertz, is barely getting a signal ratio of 2, which we saw earlier is not very good for image processing. But in the in-gas, you're already up into a signal noise ratio of 27. Now the CQD camera, even though it has bigger pixels, its lower quantum efficiency is really hurting in this case versus the in-gas camera. Now, granted, it's helping versus the small pixel pitch in-gas camera, because even though its quantum efficiency is lower, the big pixel pitch is really helping it with signal collection, and its lower read noise is helping you, especially in these low signal levels. Now, if we look at a high signal flux situation where you have lots and lots of light, the signal noise ratio, as you can see, gets much, much better. You know, at 100 hertz, you're already up to a signal noise ratio of 100 for the CQD camera. Now, granted, you're up into the many hundreds with the in-gas camera. Granted, the in-gas camera with a small pitch is still having trouble. It's in the 10s, and that's because of this high read noise for the short integration time, and also these small pixels are having trouble collecting a lot of light versus these larger pixels, which can collect tons of light. The other thing, the other notice is that because of the signal collection efficacy of this large pixel in-gas camera, you're actually saturating the pixel. You're at the limit. You can't even get to 30 hertz because it saturates somewhere between this point and this point. And the same is true actually with the in-gas camera. It's actually having the same problem. I omit the CQD camera in this case because the larger pixel pitch actually has a larger full well, and they were actually able to get to the higher signal levels. Granted, the signal to noise ratio is still lower, but that's one of the advantages. And it's important to be able to take a look at not only your signal to noise ratio, but you got to take a look at this full well capacity as well. So in conclusion, it's critical to look at your complete camera specifications. You got to look at everything: read noise, quantum efficiency, dark signal, and your pixel size, and to understand your signal to noise ratio needs. The application may demand high performance cameras, and it's important to understand the light level that's coming in and the speed you need to image. And so, as I said, happy to talk about applications if anybody wants to contact me. Thank you very much for listening today, and I appreciate your time. Thank you.
Thank you, Martin, for detailing the importance of signal to noise in SWIR hyperspectral imaging. To everyone in the audience, if you haven't already, you can type your questions and comments into the chat, and do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 4th annual Vision Spectra Conference. Thank you all so much for joining us.